And today, I'd like to continue the topic of power of randomization. Oh. So just the topic is the same. Okay. I'd like to start with some basic things for review. For review of some basic issues of probabilistic analysis. This is the most important notion, random variables. Okay. So suppose that we have a random variable x. X is a number from 1 to 6. So this is a standard notion of a variable. Variable x takes a value 1 or 2 or 3 or 4 or 5 or 6. Okay. So natural. This is natural variable. This is a natural standard notion variables. But if we say x is a random variable, then we have another thing. Meaning, we have a probability for each number. So for example, this number is a probability 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. So this is a probability. Ooh. So if you say x is a random variable, then x takes each value with probability something, like that. So this is a definition of random variable. So in this case, this exactly explains throwing a die. So if you throw a die, then the number of die will be 1 of the 1 through 6 with equal probability. Equal probability meaning each value takes probability 1 over 6, 1/6. Okay? This is just throwing a die. Maybe another random variable y. It takes value 0 or 1, probability 1/3, 2/3, for example. So this is a coin, maybe biased coin. Biased coin, so it's not a fair coin. Yeah, if it's a fair coin, then of course head and tail has a probability 1/2. But biased coin means head is more probability than tail, for example. Okay, this is a biased coin, and this is a die. Biased coin. Okay, so this is a notion of random variable, and probably the most important thing about random variables is the expected value. Expected value, E of x. Random variable x and its expected value. This is, of course, you know the definition. That is 1/6 times 1 plus 1/6 times 2 plus da 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 plus 1/6 times 6 is equal to, I don't know, is equal to 3.5. This is the expected value of the number of die. Okay? As you know, this is pretty easy. Everybody knows. And the expected value of y is equal to 2,000. One third times 0 plus 2,000 times 1 equal, of course, 2,000. Okay. Now, variable z equals x plus y. Okay. So variable z is a sum of variables x plus y. This is again random variable. It takes value 0, 1, 7. Oh, this is just like that you have a coin and die. You throw die and coin. And the variable z is the sum of two values. Okay? That's why it takes value 0 through 7. What is the probability of 0? The probability of 0 is, of course, this is a... Oops. No 0. I'm sorry. No 0. Sorry. 1, 2. Okay. So what is the probability of value 1? Value 1 should be a 1 and 0. No other cases, right? So that means the probability 1/6 times 1/3 is 1/16. 1/80. 1/80. What's the probability 2? 2 is 0, 2 and 1, 1. So for number 2 is 1, 1 is 1/6 times 2/3 plus 0, 2 is 1/3 times 1/6 equal, I don't know. So of course, you can calculate probability for each value, right? So then the question is how to get the expected value of variable z. Of course, you can calculate expected value by calculating all the probability of these values. Okay? So value is 1/18, and this value is I don't know, and this value has some probability. Then exactly like this, we can calculate the expected value. But wait. That is not a good way. That is not a good way. We have much better way of calculating this expected value. That is a very important theorem for random variables. That is linearity. So this is one of the most important. I would say this is the most important property of probabilistic analysis. It's the linearity of expectation. This comes in almost everywhere in the probabilistic analysis. Almost everywhere. So you should know, you must know this linearity of expectation, and also you should be able to use this actually for your analysis. expected value of z is equal to, of course, expected value of x plus y is equal to, this is important. The expected value of x plus expected value of y. Oh, this is very important. So, in this case, you don't have to calculate those complicated analysis probability. Just we have expected value x is 3.5 and expected value y is 2/3. That means expected value of z is just sum of these two values. Done. Very easy. Very easy. Okay? That's why this linearity of expectations is very, very important and also convenient. Example. Now example. Okay. Random variable. Random variable x. Okay. We'll be thinking random permutation of 1 through n. What is random permutation? This is, of course, for example, 1, 2. Maybe I should use a blue color. One, 2, 3, 4, 5 is a basic number, and the permutation is just a permutation of these 5 numbers. So, for example, 3, 1, 5, 4, 2. Okay, 3, 1, 5, 4, 2. This one permutation is a permutation of these 5 numbers. Okay. So what is this x? This x is a number of positions I such that sigma I is equal to I. What does it mean? Okay, so this is one permutation. One permutation of sigma. So this is a permutation. Sigma 1 is equal to 3. Sigma 2 is equal to 1. Sigma 5 is equal to, no. Sigma 3 is equal to 5. Sigma 4 is equal to 4. Sigma 5 is equal to 2. Okay? That means, in this case, the number of positions, if permutation is this sigma, then the number of positions I such that sigma I is equal to I is what? Just 1. Okay, this is sigma 4 is equal to 4. The number of positions is 1. If sigma is equal to maybe 1, 2, 5, 4, 3, then the number of positions such that sigma I is equal to I is equal to 1, 2, 3. Okay? So the x is the number of positions I such that the number does not change. Okay? So for example, in the case of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this is a basic number. Then permutation, we just write down all the permutations here. Okay? For example, 1, 2, 3, 4, 5 is a one permutation, and this is the number is 5. This number is 5, okay? All the same. All the same. So this is a 5. Then 2, 1, 3, 4, 5 is equal to 3. And maybe, I don't know, 1, no. Yeah. 1, 2, 5, 4, 3. This is again 3, and so on and so forth. Okay? The number of x is meaning, so now x is equal to 5 with probability 1 over 5 factorial. Because, all the same is only this permutation. Okay? And we have 5 factorial permutations. That's why random variable x takes value 5 with probability 1 over 5 factorial. Okay? X takes value 3 with probability, I don't know. Obviously, you can calculate. You can calculate all the probabilities by listing all the permutations. But you need a lot of work. Okay? So now I assume that you understand this random variable x. Okay? You understand? So x takes value 0, 1, n, with probability 1 over n factorial. Maybe this probability is pretty big. But the probabilities, calculating the probability is quite messy. Yeah. Now, of course, we'd like to calculate its expected value. What is the expected value of this variable x? It's totally impossible. By calculating it by all calculating the probabilities. It's totally impossible. Okay? But we have a very nice way, just by using this linearity of expectation. Introduce new. Okay. So we just introduce a new variable, x sub I. X sub I. Meaning, now x sub 1 is here. X sub 1. X sub 2. X sub 3, x sub 4, x sub 5. Okay. So for example, for this sigma, x sub 1 is equal to 0 because different. X sub 2 is 0. X sub 3 is 0. X sub 4 is 1. x sub 5 is 0. Okay? So, obviously, random variable x can be broken down into the sum of these n x sub I variables. Just look at this case. You know, random value of random variable x is just 1, but the sum of these 5 random variables is also 1, the same. Okay? So we can write this way. Now, now we can use the expectation. We can use the linearity of expectation. Then we can write this. We can write in this way. Then the sum of this expectation is equal to 1. Why? Because what is this value? What is the expected value of x1? x1 is here. x1 is here. If you can think about all random permutations, then all 1 through 5 come here with equal probability, right? So the probability that 1 comes here is 1 over 5. That is, this value is 1 over n. Is equal to 1. Really beautiful. You don't have to calculate anything about the explicit probability of each value. Just by using linearity of expectation, then we can calculate the expected value of x. So it doesn't depend on number n. Does not depend on. So for any big number n, 100 or 1 million, it's the same. The expected value of x is 1. That means if you can think of a random permutation, then on average, one position is the same. On average. It's interesting. Okay, now if you're doubting, you have a doubt, then just you can do a computer experiments. Something like n equals to 20, then you can generate a lot of random permutations. Then just look at each permutation. On average, one position is the same. Good. Now I'm going to the next example. Example 1, example 2. So randomize quicksort. This is very important. This is very, very important because analysis of quicksort is very important, and many instructors, many professors of algorithm courses say this is a highlight. This is a highlight of the course. So if you visit, for example, the famous professor's lecture, online lecture, at MIT or Stanford or maybe there's many famous universities, then you can see the video of the lectures. Then probably you can find that the instructor says that today we are going to highlight of this course, that's the analysis of Quicksort. Yeah. Usually it takes time. It's not so easy. So for example, one example is a professor at MIT, then he takes more than 1 hour, something like 70 minutes, even more, just explaining the analysis of Quicksort. Today, I'm gonna do that. I will give you the analysis of Quicksort just maybe 20 minutes or maybe 25. Yeah. Much quicker and much simpler. Okay. So let's start. What is Quicksort? Quicksort is, of course, you know Quicksort. 5, 3. This pen is bad. Also bad. Better. Okay. What is Quicksort? Quicksort is you are given a sequence of numbers, then just pick one number at random. Just pick one number at random, maybe 7. This is called pivot. Then what you do is to compare all other numbers with this 7 and divide it into 2 groups, less than 7 and greater than 7. Okay? So now we have 2 groups, 5, 3, 1, 4, 6, and 8. So this is smaller than 7. This is larger than 7. So we have 2 groups, and do the same thing recursively. Exactly do the same thing recursively. Next, maybe your pivot is 3. Then 2, 1, and 5, 4, 6. Then pivot is 2, then 1. Your pivot is 5. Okay, you pivot is 5, then 4, 6. Okay, so we are done. We have done sorting. That means, 1, 2, 3, 4, 5, 6, 7, 8. We have done the sorting. Okay? So just let's look at this sorting process. So this is, of course, it's a kind of a random sequence. But, for analysis of this Quicksort, we can assume that the given sequence is already sorted. Nothing different. I'll show you. So suppose that the sequence is already sorted. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And suppose that you choose the same pivots. Okay. Then you first choose 7, then the 1, 2. Then again 3. The pivot sequence is the same. 7, 3. Okay? Now, the execution of the sorting looks exactly the same. Okay? Now you choose 7 for the pivot. Then you compare all the other numbers with 7 and divide them into 2 groups. Exactly the same. Exactly the same. Okay? So this is much, much easier for analysis. So we are assuming that the number is already sorted. Okay? Now, as we consider pivot sequence. Is equal to, in this case, 7, 3, 8, 2, 5, 1, 4, 6. So this is pivot. And this is only one number, but we also think this is also pivot. Only one number, but this is also pivot. So pivot 2, 5, 1, 6, 1, 4, 6. The sixth pivot is 7, 3, 8. Or maybe 8 might not be this position because of this that only maybe 8 might be here. It's not so important. But 7, 3, 8, 2, 5, 1, 4, 6. This is a pivot sequence. That means this sorting process can be completely described by a pivot sequence. Okay? So, the sorting process, execution, one explicit execution equal pivot sequence are not equal. If we are given explicit execution sequence, then we can get a pivot sequence. But pivot sequence, this is a random permutation. It's a permutation, sorry. Permutation of 1 through 8. Okay? And as I said, so if we are given explicit execution, then we can obtain, this is kind of, this is interpreted to, we are given a explicit pivot sequence. But the important thing is the other way around. It's the same. We are given a pivot sequence, then we can define an explicit execution sequence of the sorting. Why? Let's see. Suppose that sigma is equal to 2, 6, 1, 8, 7, 2, 6, 1, 8, 3, 4, 7, 5. This is a permutation. Then we can define execution sequence. Let's do it. 1, 2, 3, 4, 5, 6, 7, 8. Okay? First pivot is what? 2. Then 1, 3, 4, 5, 6, 7, 8. The second pivot 6. Okay? Now 3, 4, 5, 7, 8. Third pivot is 1. Okay, we are done. And the next 8. Then, this is a 7. Now 3. Then 4, 5. 4, 5. And 7, 5. Okay? So this is the execution sequence of Quicksort. That means we are given a pivot sequence, then, kind of one-to-one correspondence between pivot sequence and execution sequence of Quicksort. Okay. Suppose that. Okay. So selecting pivots. So we assume this is almost obvious, but maybe we need some assumption. But it's almost obvious that if we select pivots at random, then that corresponds to a random pivot sequence. Random pivot sequence. That means random sorting, random quicksort is completely described by random pivot sequence. Okay? So probably maybe this part is a little bit, but intuitively this is okay. Intuitively this is okay. Maybe for formally speaking, we need some proof of this part, but intuitively I don't omit the proof, but intuitively this is okay. Once again, if you are given a random pivot sequence, then that completely describes the execution sequence of Quicksort. Okay, now we start analysis. We are ready. We are ready to do analysis. We are given a random pivot sequence sigma, then what is the computation time for that sequence sigma? Okay, this is T sigma. Is almost equal. Is the number of comparisons of two numbers. Okay? I'll explain. So this is a given pivot sequence. Then this is a execution sequence of the Quicksort. Now, first pivot is 2. First pivot is 2. Then you need to compare all the other numbers with 2. So the number of comparison is 1, 2, 3, 4, 5, 6, 7. Right? It's the number of comparisons. Then we have 2 groups. Then the next pivot is 6. Then the number of comparisons is 1, 2, 3, 4, 5. Okay? The sum of all those comparisons is the number, is the computation time, roughly speaking. Roughly speaking. Okay. So let's calculate the number of comparisons. Here. Oh, by the way, I'll give you some intuition. But this is a sequence of input. If the first pivot is almost middle, then the sequence is equally divided into 2 sequences, almost the same length. Okay? What is the number of comparisons? This is almost n. Actually, n minus 1. Here, again, your pivot is almost middle. Then what is the comparison here? Almost n. Because it's an n over 2, the sum is n. Okay? And then again, this is almost n. What is the depth? Log n. Okay? Because it's always halving. Then the depth height is n. That means the total comparison is something like n log n. Something like n log n. But wait. This is a good case. Right? Because all the pivots are chosen almost in the middle. But maybe the worst case, the pivot is pivot is selected here, and then the one group is big, the other group is very small. Again, the pivot is not the middle, but near to the end. Then the depth is n. Then the number of comparisons is not n log n, but n squared. So completely non-trivial, the analysis of Quicksort. Okay? So the worst case is a pivot is like here, then very small and almost the same. And again, pivot is here, then very small and very long. N, almost n squared. Yeah. Now random variable comes in. Now, we define random variable xij. Okay? Xij is equal to 1 if number I and number j are compared under this pivot sequence sigma. And 0 if I and j are not compared under sigma. For instance, this is bad. Maybe I'll try this pen. Okay, we have 8 numbers as before. And let's assume I is equal to 3 and j equal to 7. Okay. Now, suppose that our sigma, our pivot sequence is 2, 6, 1, 8, 3, 4, 7, 5. Then I and j, 3 and 7 are compared or not. 3 and 7 are compared or not. Answer. Yes or no? Compared or not compared? It's easy. Why not simulating the Quicksort? The first pivot is 2. First pivot 2. Okay? Then nothing. Nothing. Nothing to do with 3 and 7. The next one 6. 6 here. Then those two guys are divided. That means never compared. Right? What about this? Now the pivot states are 8, 3, 7, 1, 5, 2, 4, 6. This time, 3 and 7 are compared. Why? 7 comes first. 8 is nothing. 3, I'm sorry. I made a mistake. 3 comes. Okay? Actually, no, that's okay, that's fine. That's fine. Okay? 8 and nothing. But 3 is important. Now 3 is a pivot, and 3 and 7 are compared. Okay. So the question is, when you look at sigma, which number in 3, 4, 5, 6, 7 comes first? That is important. Okay? If those 3 guys comes first, 4, 5, 6 comes first, then 3 and 7 are not compared. If 3 or 7 comes first, then they are compared. And those 4, 5 numbers are equally likely to come first in sigma, because sigma is a random sequence. Sigma is a complete random permutation. So it's completely equally likely which number comes first. That means we can calculate the probability of xij is equal to 1 as this. So this is a number of numbers, 5. Okay? 3, 4, 5, 6, 3, 4, 5, 6, 7 are 5 numbers, and 2 is this guy and this guy. Okay? So we have 5 numbers, and 3 or 7 comes first, then they are compared. So this is a probability. So we are done. Then, after that, it's just a simple calculation. Okay, so it's xij is a random variable such that I and j are compared or not. Okay, so we sum up all those variables, then we can get the total number of comparisons. Again, we use the linearity of expectation. Again, this is always comes in. Linearity of expectation. Because our random variables takes just 1 or 0. 1 or 0, that means this value is a probability of xij equal to 1. Then I just plug in this value. Then okay. So this is a case. I is equal to 1, j is equal to 1 through n. So I equal 2, j equal 2, n, and so on and so forth. We sum up all I and j. Okay. If I is equal to 1, then j can be 1 through n. If I is equal to 2, then j can be 2 through n. And you already know that this part is log n, almost log n. And this is all log n and log n. So that means it's almost. Oh, no, I'm sorry. It's up to. 2 times n log n. This is big O, n log n. Okay. So expected value of computation time is n log n. Well, if we say the expected value of the computation time is n log n, it does not directly mean our computation time is always n log n. But with high probability, our computation time is something like n log n. Maybe 3 times n log n or 5 times n log n. But there is high probability. It's something like n log n. Okay? Good. So this is we're done about the analysis of Quicksort. It's a very beautiful analysis of Quicksort. If you visit some textbook of algorithms, then many of them include analysis of Quicksort. But probably, you will notice that the analysis is quite complicated, much more complicated than this. Yeah, but this analysis is very clever, very clever. Of course, this is not my analysis. This is done by other guy, and I just found this analysis in the net. But this is very clever. Yeah. Good. Okay. Now, I'll show you another example. Unbalancing lights game. Let's have a fun. No, it's fun. Okay, we have given this thing. Okay. We have n by n mesh. N by n mesh. And we have n squared. N squared lights at each grid point. So those red one are lights. And 2n switches. 2n switches. So this is a column switch. This is a row switch. Okay? You know, my drawing is bad. My picture is bad. But the switch is a so-called, push switch. Switch is a so-called alternating switch. Alternating switch. So each switch is, if you push, flips. If you push, that flips on and off of that row or column. So for example, if you push this switch, then look at this column. Then if the light is on, then change to off. So just switch on and off of this column. You push this one, then completely switch on and off of this column. You push this switch, then completely change, completely swap, completely switch on and off of this row. Okay? You understand? Now again. Again. Suppose that we have a 100 by 100 mesh. That means we have 10,000 lights. Okay, prize money. So you attend if you play this game, and if you win, then you can get this prize money is equal to so your prize money you play this game, then you can get the prize money. That is the number of on rights minus number of off rights, US dollars. However, you have to pay 100 US dollars to play this game. And maybe you have 10 minutes. To manipulate. Manipulate. Okay, so this is a game. By paying $100, you can play one game, then you are given 10 minutes. Using that 10 minutes, you can manipulate all those switches as you like. Then after that, you get the money. Its amount is the number of on rights minus number of off rights. US dollars. Okay? Of course, the initial rights, initial situation is very important. Okay? If the initial rights are all on, then of course you do nothing. Then you can get 10,000 US dollars. What about if the initial station is all off? All off. Again, easy. Push, 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 push. Then it changes all on. You get again 10,000 US dollars. Of course. That's why initial situation should be complicated. Should be complicated. Maybe you are given the initial rights one half on, one half off. Maybe. Furthermore, you look at this row, again, 5 on and 50 on, 50 off. Look at this column, again, 50 on, 50 off. This row, 50 on, 50 off. You push this button, nothing changes. Would you like to play or not? Is it worth to pay? Is it worth to paying $100? Okay, let's do analysis. Now I have theorem. Okay. Now we have this theorem. Now we're using +1 and -1. And probably you can easily tell that +1 means on, -1 means off. Okay? And for any given aij +1 or -1, that is the initial on and off. Initial on and off. For any initial on and off, we can select the value of xi and yj. Yeah, this is a switch. So maybe this is xi. And this is yj. Switch. We can select the value of the xi and yj, again, ±1, such that, what is this value? What is this value? Suppose that this is a, let's say this is x, this is a, look at this right. Look at this right. Initial value is aij. Okay? And if you push this switch, then xi is equal to 1. No, xi equals -1. Okay. So. Okay. Okay? So if you do not push switch, then it doesn't change. Doesn't change. If you push again y, this is y, then again y is not pushed, then it doesn't change. If you push, then it changes minus. Okay? This is exactly, after you manipulate switches, whether or not this light is on or not. Okay? So all the sum is equal to exactly this number. Exactly this number. Is at least this value. Is at least this value. For any initial configuration. For any initial configuration, you can, there's a way of manipulating your switches such that you can achieve this value. What is this value? What is this value? This is something like 0.4. And this is something like, this is 1,000. If n is 100, right? We are now at 100 by 100 switches. This is n equals 100. Then n to the 3 halves is 1,000. And this is 0.5, meaning you can get 400 US dollars. You must be able to get 400 US dollars. Good. But the question is how to manipulate your switches. This theorem says this is a way of manipulating switches, but this theorem says nothing about how to do that. How to do that? But the algorithm is very easy. Okay, I don't have much time, then from now on, it's a little bit quick, but there's almost calculation. Okay, so look at ice law. Okay, look at this law, ice law. Then the switch is y1, y2, y3. Okay, what you do is just select y1, y2, y3, yn completely at random between plus and minus 1. Just, completely at random. You push the first switch with probability 1/2, same thing, same thing, same thing. Okay? Just, flip a coin. Flip a coin, well, head, okay, push. Flip a coin, head, push. Tail, not push. Okay? It's pretty easy. Oh, this is a value. This is a value you can get from this row. From this row. After randomly selecting y1 through yn, then you can get your bonus, your money from this row, ith row. Okay, this is this one. Ah. Okay. Now, for some reason, I'm going to consider not Ri itself, but the Ri, absolute value of Ri. Ri, your bonus might be minus, might be negative, right? Because it is what you do is just randomly selecting y1 through yn. Then your bonus, your money might be minus. But, let's consider absolutely value. Absolutely value, and R is the sum of all the rows. Okay? So this is not your bonus. This is not your bonus, because your bonus might be minus somewhere. But remember, you can also manipulate this switch, right? That means after manipulating this y1 through yn, if this row is minus, what would you do? Just push this one, then make it plus, right? So actually, this is what you can get. This is what you can get. Okay, so let's calculate this R. Okay, so this is a this is sum of random n values, plus minus 1. Then this is a famous binomial distribution, like this. The average value is, of course, 0. And the distribution looks like this, bell curve. That is what we call bell curve. So if you don't know this, then this is very important to visit some textbooks about the probability. Then, any textbook should mention this bell curve, binomial distribution, or normal distribution. Now, we see expected value of Ri. Absolute value. Expected value of absolute Ri. Ri. This is a okay. So this part is, maybe if you don't know this kind of bell curve, then this might be a little bit hard to understand. But this is what we call standard deviation. And this is the expected value of this is exactly, here. Here, oh, I'm sorry. Is the value x. That is the area is the same. Area is the same. So this is kind of a, this is a most likely deviation. Okay. So of course average is 0, but almost always it's not 0. In many cases you have a deviation. This is average deviation x. This is average deviation. Average deviation x is there is a theory. There is a theorem. So I omit this theorem, but that deviation is almost the same as standard deviation. Standard deviation. Okay? A little bit what? So I don't know. A little bit smaller than standard deviation, but almost a standard deviation. And just, calculation. This is a standard calculation. This means okay. So expected of this value, expected value of this random variable R is exactly this value. Exactly this value. Okay, so we are done. We are done. Because the expected value of this R is exactly this value. This value. That means there must be a way of selecting xi and yi to achieve this value, because this is the expected value. Okay, and this is a simple argument. And as I told you, this is exactly what you can get. What you can get. Okay, we are done. I said that this theorem says nothing about your strategy. Nothing about your strategy. But in this proof, I gave you your strategy. Your strategy is very simple. Just select y1 through yn at random. Okay? Then you look at each row. Okay, the first row is plus. No, it's fine. It's fine with you. The second row is minus. Oh, no good. Then you push switch. Then you change exactly minus to plus. Right? Do the same thing. The same thing. Then you can get this value. On average. expected value of your revenue is exactly this value. That means, you know, the gameplay money, $100 is cheap because expectedly you can get $400. Good. Okay, so we are done with today's lecture. And as I said, the next week is off. No, the next week's class is cancelled, will be cancelled. Okay? So I'll see you 2 weeks from now. And the next lecture, I will still stay on this kind of randomization, but again, I'll show you a very interesting topic that is called random walk. It's really interesting. Okay, so see you 2 weeks from now.